thank you for joining us on Synthesis Workshop. I'm Kathleen Cheasty and a member of the Synthesis Workshop editorial team. Today we are joined by Diana Cavalli, who will be talking about the photocatalyzed synthesis of lactones and lactams via a cyclization alkynylation cascade. Diana completed her PhD at EPFL in the group of Jérôme Vase and is now working in the Bernades lab at the University of Cambridge as an SNSF postdoctoral researcher. And from there, I'll hand it over to you, Diana. Thank you for joining us today.
Thank you very much for your kind introduction. It's a pleasure to be here to present our work on the photocatalyzed synthesis of lactones and lactams via cyclization alkynylation cascade. Photocatalysis is the field of organic chemistry which uses light to promote a chemical reaction. And to do so, we're using photocatalysts. The more classical ones are iridium or ruthenium-based metal complexes. However, over the years there has been an increased use on the organic dyes as a more sustainable and economical alternative. Upon light absorption, one electron of the HOMO will be promoted to the LUMO, making the excited state photocatalyst at the same time a better oxidant and a better reductant. This property of the excited state photocatalyst is used to activate the substrate via single electron transfer, in which the dye undergoes oxidative or reductive quenching, generating the desired radical intermediates. Alkynes are versatile functional groups. They can be found in many bioactive compounds as spacers, active moiety, and linkers. Additionally, they can be found in many intermediates because they can be further functionalized via cycloaddition, reduction, hydration, or metathesis. It's therefore highly appealing to directly introduce alkyne moiety in radical reactions, and our group focuses its attention on the use of ethinyl benziodoxolones as somophile in radical alkynylation reaction. Lactones and lactams are also found in many bioactive compounds, and because of this, there has been many methods for their synthesis, mainly relying on the direct construction of the carbon-oxygen bond. The more classical examples are esterification, Baeyer-Villere oxidation, and metal-catalyzed cyclization of a carboxylic acid into an olefin. On the other hand, the 5-exoteric cyclization of an alkoxylic carbonyl radical intermediate is a complementary approach to construct this motif. In fact, the starting material can be easily accessed from homolylic alcohols and then activated, introducing a redox active group. Additionally, the radical intermediate formed after cyclization can be further functionalized using a somophile. Lactonization reactions using this approach were reported starting from selenocarbonates, Barton estering xanthates under classical conditions for the generation of radicals, and then the radical intermediate was functionalized with a hydrogen atom or a sulfur moiety. More recently, Overman and co-workers described this metallophotoredox catalyzed synthesis of lactones starting from easily accessible cesium oxalates using an iridium photocatalyst and a nickel co-catalyst to directly introduce the aryl or vinyl moiety, and they mainly focus on the synthesis of spirolactones. Therefore, our approach was to broaden up the scope of the reaction by introducing an alkyne moiety using EBX reagents. Also, we wanted to replace the iridium photocatalyst for an organic dyes because it's a more sustainable option. And we also wanted to expand the scope beyond Heterocycles and not only to the construction of lactones but also lactams. We started our investigation using this cesium oxalate as starting material, 1.5 equivalent of phenyl EBX as somophile, 5% more of 4-CZIPN as an organic dye, in dichloromethane with a concentration of the starting material 0.1 molar, and we irradiated with a Kessel lamp with the irradiation center at 440 nanometers, and overnight we could see 53% of this spirolactone forming. Then, by replacing 4-CZIPN for its stronger oxidizing version, the chlorinated one, we could improve the yield to 64%. Also, we could replace the chlorinated solvent for DMSO because it's a non-toxic solvent, and we lowered the catalyst loading without affecting the yield. Then, because we were seeing a lot of polymerization of the starting material, we lowered its concentration to 0.05 molar, and we increased the loading of phenyl EBX, which gave us 75% of the desired product. To further slow down this reaction, we lowered the intensity of the lamp to 22 watt, and in this case, to achieve full conversion, we needed to steer the reaction longer for 42 hours, which gave us 80% of the desired spirolactone. Then we also performed some control reaction. Without using any photocatalyst, the spirolactone was formed in 14% yield due to the photooxidative property of phenylBX, which we described in a previous paper. And finally, without any light, no product would be observed, confirming that the reaction proceeded via photomediated mechanism. Having established the optimal reaction conditions, we moved our attention to the scope of the reaction, and we started with the cesium salts. Our model substrate cyclized in 76% isolated yield, and we were also pleased to see that we could scale up the reaction in 3 millimole scale in batch without affecting the yield too much. Regarding the spirocycle, we could vary it a lot. We could introduce various heteroatoms and vary the ring size. And also we could perform the reaction on this dihydroepiandrosterone derivative, obtaining this lactone in 50% yield. Also, we wanted to apply the reaction on secondary alcohols and not only focusing on spirolactones as mentioned previously. Toward the light, we could obtain this lactone having a pendant homobenzylic chain in 55% yield. And we could also form these bicyclic compounds in the perfect diastereoselectivity. Also, we were pleased to see that we could form this 6-cis spirocycle by using an homologated version of the cesium salt. Then we wanted to see the effect of the type of radical intermediate formed in the reaction, going from a primary radical to a secondary and a tertiary one. So we started with this fully unsubstituted homoallylic cesium oxalate, which cyclized in 62% isolated yield. Introducing an ethyl group on the double bond and hence generating secondary radical produced the product in 70% yield. However, the product formed from a tertiary radical was obtaining only 40% yield, and we speculated that the intermediate in the reaction was a little bit too sterically hindered for the phenylBX to properly attack. Then we applied the same reaction condition to the generation of lactams, and we were pleased to see that we could obtain this tosyl product 1 in 71% yield. And also we could vary the type of lactams, also having an ethyl group, forming also spirocycles, and performing this reaction on this celecoxib derivative. However, the tosyl group was crucial for our reaction. In fact, other type of protecting group didn't generate the desired product, but the product formed after direct alkylation of the amino-carbonyl radical intermediate. And we speculated that this type of compounds didn't adopt an optimal conformation for the cyclization. Then we moved our attention to the scope of the EBX reagents on both lactones and lactams, and we're pleased to see we could introduce halogen on the ortho and meta position, and also the para position could be varied a lot, going from slightly electron donating methyl group to electron withdrawing group, such as trifluoromethyl and methyl ester. Then we also performed some product modifications. After reductive opening of the lactone, we could obtain this 1,4-diol with a pendant alkyne group, and we could also oxidatively cleave the triple bond to obtain this carboxylic acid in 70% yield. Additionally, subjecting this diastereomelically pure lactone to the condition for the reductive opening gave this 1,4-diol with 3 adjacent stereocenters. Based on literature precedents and some mechanistic studies we performed, we could propose the following reaction mechanism. Lett irradiation would generate the excited state photocatalyst, which then undergoes reductive quenching with the oxalate to generate this oxygen center radical, which it then undergoes very fast decarboxylation, followed by 5-exotrig cyclization to generate this key intermediate for our reaction. The latter reacts then with phenylBX to give our product, and this iodine radical intermediate, which is responsible for turning over the photocatalyst and generating this iodobenzoate. So to conclude, in this work we developed an organophotoredox catalyzed synthesis of functionalized lactones and lactams from easily accessible homoallylic alcohols and amines, and we applied this method to the synthesis of spirocycles as well as fused and bridged bicyclic compounds. Finally, I would like to thank my PhD supervisor, Professor Jérôme Waser, and the whole LCSO group for their support over the years. I would also like to thank EPFL and CCR Catalysis for their financial support, Matt for giving me the opportunity to present my work here today, and to all of you for your attention. Thank you very much.
Thank you for joining us for this Research Spotlight episode, and thank you, Diana, for sharing your chemistry. If you enjoyed this episode, consider subscribing to our YouTube channel and see you next week.